Hello, today I'll be going over another problem from Energizing Physics Lesson 4.5. So this question asks, if Miranda bends down and jumps straight upward, what will her motion graphs look like given the velocity versus time graph? So the first graph we'll draw is acceleration versus time. Since we're given her velocity versus time and we know that the acceleration is basically just the slope of the velocity versus time graph, we'll look at certain coordinates. So the first period we can look at is from 0 to 0.2 seconds. And we see that the acceleration is going to equal delta v over delta t, which is equal to negative 1.5 over 0.2, which is equal to negative 7.5. Next, we look at 0.2 seconds to 0.3 seconds, and we know acceleration will be 0 because the velocity doesn't change. And then the next period we look at is approximately from 0.3 seconds to 0.55 seconds. And we see that the velocity goes from 3.5 minus negative 1.5 to, and the delta t is 0.25. So this is equal to 5 over 0.25, which is equal to 20 meters per second squared. And then the final period we look at is 0.55 seconds to 0.9 seconds. And we know that the delta v is going to be negative 3.5 and delta t is going to be 0.35. So a is equal to delta v over delta t, which is equal to negative 3.5 over 0.35, which is equal to negative 10 meter per second squared. So now we can go to that actual graph where we will plot this. So we're just filling in the increments right here. And a good increment to use would be 2.5. So between 0 to 0.2 seconds, we are at negative 7.5. So this is the magnitude of our acceleration. And then from 0.2 to 0.3, we go to 0. So that's this period here. And then at 0.3, we go to 20 meters per second until 0.55 seconds. So that's up here. And then at 0.55, we come back down to negative 10. And we continue all the way to 0.9. So this is our acceleration versus time graph. It's pretty chaotic. But next we will do F net versus time, and we can examine our accelerations using and to get F net, because F net equals ma, and we know Miranda's mass is 50 kilograms. So from at the same period, from 0 to 0.2 seconds. So one trick to drawing these graphs is we know the general shape of F net and A will be the same because they're directly proportionate, and the slope, the only difference is the mass. So we can draw the general shape again. So if we go from the labels, from 0 to 0.2, it's going to be negative here. And then from 0.2 to 0.3, it's going to be 0 again, because that's what we saw from the acceleration graph. And then from 0.2 to 0.55, it's going to be at its max. So 0.3, this is 0.5, so 0.55 is here. and then it's gonna come all the way down again, all the way till 0.9. So that's going to be the shape, because it's going to be the same shape as acceleration, but the magnitudes will plug in using multiplying by mass. So when acceleration was negative 7.5, we'd multiply 7.5 times 50, which is the mass, so that's negative 375 newtons there. And then at 0, it's going to be 0, and when it's at 20 meters per second squared, we're going to multiply 20 times 50, which is going to be 1,000, which is its max newtons. And then when it comes back down to negative 10 meters per second squared, that's going to be negative 500 newtons. Now, next we're going to draw the position versus time graph, and for this graph we're going to just use the initial velocity versus time graph that we were given in the beginning. So with this, we're going to use the areas under the curve. So we look at from 0 to 0.2 seconds, we can see that the triangle area is going to be 1/2, 0.2, and then 1.5. And this is going to be a negative, equals delta x, which is going to equal to negative 0.15. And then from 0.2 to 0.3, it's going to equal to 1.5 times 0.1, which is equal to delta x, which is negative 0.15 again. And then from 0.3 to 0.4, we're going to see a delta x of 1/2, 0.5, 0.05, and then 1.5, which is going to be half of them, which is negative 0.075, and then from 0.435, sorry, this is 0.3 to 0.35, and then from 0.35 to 0.55 is equal to 1/2, 0.2, and then 3.5, which is equal to 0.35 delta x. And then from 0.55 to 0.9, it's equal to 1/2, 0.35 times 3.5, which is equal to 0.6125. So those are the numbers and the delta x's, and then we plot them in the graph to obtain the x versus time graph. Okay, so now that we have the values for the delta x's over the certain periods, we're going to plot these points to get the position versus time graph. So this is going to be time in seconds, and this is going to be x in meters. So we see that from 0 to 0.2 seconds, she travels negative 0.15 meters. So that's from 0, starting from the origin. And then we notice that we're going to go to this point, but her path isn't going to be linear, because we see that her velocity is linear, which means that her position is going to look like an x to the second power graph. So you see this curve. So she's moving faster at a faster speed, which is a negative velocity, which is why the x position changes more rapidly between, like, when you get closer to 0.2 than when it started. So next we go to the 0.2 to 0.3 time margin, and we see that she's moving at a constant velocity at that time, so this is going to be a linear change to negative 0.3. And then she changed from 0.3 to 0.35 seconds. She has a change of negative 0.075 meters, and we see that throughout this time period, she gets closer to velocity 0, so this is going to be a slowdown. And so the tangent to this part of the graph should be 0 because that's the velocity at 0.35. And then from 0.35 to 0.55, she has a linear velocity that becomes more, because that's positive, and that is going to increase 0.35, and also the velocity gets faster throughout the period, so we see the delta x becomes steeper. And then finally, between 0.55 to 0.9 seconds, she goes 0.6125 meters, and it also gets closer. Her velocity approaches 0 until 0.9, so the slope also becomes less steep for the position graph, and it ends at 0.5875 meters. So this is 0.5875 meters at 0.9 seconds. So there we have her position versus time graph. So the next question is asking for her force diagram, and we actually can use so they want a force diagram at 0.1 seconds, and then 0.25 seconds, 0.4 seconds, and 0.7 seconds. So we already did the F net graph over here, which is this one. So we can look at 0.1 seconds. Well, that's going to be when her force is over here. Her net force at 0.1, the net force is going to be negative 375 newtons. And at 0.25, her net force is going to be 0 newtons. And then at 0.4 seconds, her net force will be 1,000 newtons. And then finally, 0.7 seconds, her net force is going to be negative 500 newtons. Okay, so now that we have this data, we can draw her force diagrams. So we know that she is 50 kilograms, and we know that force of gravity is going to equal to mg. So we know that it's going to be 500 newtons. And since her net force is going to be negative 375, we know her normal force is going to be 375 less than her force of gravity. So Fn is going to equal to 500 minus 375, which is equal to 125 newtons. Now at 0.25 seconds, her net force is 0, so that means normal force and force of gravity are going to be equivalent. And then at 0.4 seconds, her net force is 1,000. So that means her normal force is going to not only overcome the force of gravity, but be much more than it. So if normal force is going to equal to 500 plus 1,000, which is equal to 1,500 newtons, whereas Fg is still 500 newtons. And finally, her Fg is going to equal 500 newtons, but her net force is equal to negative 500, so that means there's no normal force, which makes sense because she is in the air, so she's not making contact with the ground. Notice how throughout all of these diagrams, her force of gravity does not change because it doesn't change. So yeah, that is question from Energizing Physics 4.5.